There are three basic types of bonds: ionic, covalent, and metallic. And today we're going to focus on covalent bonds. Imagine two little hydrogen atoms just hanging out. Their lonely little electrons are swirling around, doing their thing. Then an oxygen atom comes by, and these three atoms get an idea. If they form bonds by sharing electrons, they're happier. Aww. Okay, so they don't really have feelings. By happy, I mean they have full valence shells. A valence shell is the outermost energy level that contains electrons. Each of the hydrogen atoms only have one valence electron, but the oxygen atom has 6. In order to maximize their stability, they want to have a full valence shell. So, each hydrogen wants an extra electron, and the oxygen wants 2 extra electrons. But how did I know that? Let's look at the first energy level. It can only hold up to 2 electrons. Why? It comes down to magnetic fields and something called spin, but for now, understand that this is the maximum amount possible. The next energy level can hold up to 8 electrons. See how I've placed the electrons one at a time in the 4 cardinal directions, and then made the electrons sort of pair up? There's a reason for that. I'm hinting at the Pauli exclusion principle, and again, it has to do with spin. It also helps us later when we want to see which electrons will be active in forming bonds. The third energy level will also hold up to 8 electrons, and now it's happy. Argon has an atomic number of 18. So it can hold all of these 18 electrons. It has a full octet, which means it's stable and it's not going to react because it's got a full valence shell. Now let's try something else. Let's try zinc, and we'll keep filling it up because its atomic number is 30. So we're at 18, so we've got 19, 20, and then it's going to get weird. It does something that I like to call backfilling. So right now we're at 20. 21, 22, 23, 24, 25, 26, 27, 28, 29, 30. That was weird, huh? The third energy level, it turns out, can actually hold up to 18 electrons, but it only does that after it gets past calcium. So zinc, strangely enough, only has 2 valence electrons. Transition metals are special in that way. Don't worry about them too much. They're easier to use than they may seem now. That last energy level can also hold up to 18. And it gets even weirder. After lanthanum, it can hold up to 32. I think it's time for a shortcut. It's Lewis dot structure time. With Lewis dot structure, you draw the valence electrons around the element symbol. But first you need a way to quickly tell how many valence electrons there will be. The families of the periodic table make it really easy to know the number of valence electrons. The alkali metals all have 1, alkaline earth metals have 2, borons 3, carbons 4, nitrogens 5, oxygen 6, halogens 7, and noble gases have 8. Now we're ready to draw. Let's start with lithium. It's an alkali in column 1, so it gets 1 dot to represent its 1 valence electron. Carbon. It's in column 14 and has 4 valence electrons, so you draw them in. But what if there are more than 4? Let's try oxygen. 1, 2, 3, 4. Pair up the electrons after 4. 5, 6. This helps you quickly see that oxygen only wants to make 2 bonds. You can use electron dots to see how a covalent bond will form. Here's hydrogen. It has 1 valence electron and only needs 1 more to be happy. Remember, the first orbital can only hold 2. Rearrange the dots to look like pairs, and you have a bond. Each hydrogen feels as though it has 2 electrons of its own. The bonds can also be shown with a simple line, which represents the 2 electrons. Let's try another one. Fluorine is a halogen, so it will have 7 valence electrons. I'm going to look ahead and see where the lonely electrons will probably go. Those lonely electrons will form a covalent bond. Again, we can leave it as it is, or replace the 2 bonding electrons with a line. Around the outside of the fluorine atoms, we can see the unshared pairs of electrons, which are not part of the bond. The BrINClHOF twins will all have those kinds of bonds, covalent bonds. Who the heck are the BrINClHOF twins? Bromine, iodine, nitrogen, chlorine, hydrogen, oxygen, and fluorine. Whenever you see them in their elemental form, they're actually bonded to themselves. They are diatomic molecules, where di means 2. For example, the air you breathe contains diatomic nitrogen and diatomic oxygen. Did you notice something about the number of bonds between them? Diatomic nitrogen contains a triple bond, and oxygen contains a double bond. Their octets are still full. Each nitrogen feels 2, 4, 6, 8 electrons in their valence shell. And each oxygen feels 2, 4, 6, 8 electrons in its valence shell. Let's try something a little more challenging. Carbon dioxide. We'll start with carbon because it has the most single electrons out of carbon and oxygen. The one with the most single electrons usually goes in the middle. Now add the oxygen atoms on the sides and put the single electrons toward the carbon because we know they want to pair up. Match up the electrons and see the bonds form. There are 4 bonds here. But let's clean this up. On paper, this is when an eraser is awesome, or just redraw it. The bonds become clear and so do the unshared pairs. Symmetry is key. Let's name some binary molecules! Just saying that out loud gives you 10 nerd experience points. This awesome word means that there are 2 parts. In computing, it's a 0 and a 1. In chemistry, it's the 2 parts of a name. Dinitrogen pentoxide, 2 words. Coincidentally, it also sounds awesome. You add "ide" to the second word, but the really great thing about covalent compounds is that the name gives away the formula. Di means 2, and pent means 5, so this is N2O5. These are the prefixes for the first 8 numbers. Only use mono with oxygen. And remember, there's no sex in chemistry, so don't try to say sexto, it's hexa. It's Greek, not Latin, for that one. The formula for carbon monoxide is CO. Carbon dioxide is CO2. Dicarbon tetroxide is C2O4. This is the naming convention for any binary compound made with nonmetals and some of the metalloids. So all of these follow the same rules. Hydrogen fluoride is HF, dichlorine heptoxide, Cl2O7, and dihydrogen monoxide is H2O. No one says that though, just say water. The same goes for methane and ammonia. Those common names are more acceptable than the binary naming. Let's practice putting together slightly more complex molecules, like CH3OH, aka methanol. Look at how many bonds will be formed. Carbon gets the middle as usual. I like to draw lines of the bonds to help me see how this puzzle will come together. The formula itself is also giving me a hint because it didn't write all the hydrogens together. One of them is probably going to attach to the oxygen. Let's try it out. And then check each one. Each hydrogen wants 1 bond, so 1, 1, 1, 1. Oxygen wants 2, there they are, and carbon wants 4. Sweet. Show unshared pairs if you want it to be a Lewis dot structure. Sometimes there's more than one way to build the molecule. That's called an isomer. Let's try it. C4H10. Carbon's in the middle. Here's where you have some choice. They can go in a straight line or a branch. Hydrogens float around it, there's no choice there. Let's try the straight chain first. Connect the carbons. Then draw the rest of the bonds that you'll want to make. Add in the hydrogens. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. If you have the right amount, sweet. If you don't have enough, that means there will be a double bond between 1 or more of the carbons. Let's draw the isomer of this molecule. This time, 1 carbon will branch from the middle. I'm going to draw the bond to that carbon just a little longer so I have room to draw the hydrogen atoms later. This is not realistic. The bonds will be the same length, but for this video, I need to draw them a little differently. Give every carbon 4 bonds and sprinkle with the 10 hydrogen atoms. This isomer has a different structural formula even though the chemical formula is the same. That's what makes it an isomer. C10H22 has 75 isomers, so the next time you're bored, you can just find all 75. Let's try drawing a polyatomic ion. CO3 2-, the carbonate ion. Start with carbon in the middle and place the 3 oxygen atoms around it. Right away, I can see that one of the oxygens will have a double bond because carbon needs to make 4 bonds, but there are only 3 other atoms. Which one should get the double bond? Well, the truth is they could all have it. This will be a resonance structure. For now, just pick one. Now for some math. 1 carbon with 4 electrons, 3 oxygens with 6 electrons each, plus 2 electrons, because it's a -2 ion, gives us 24 electrons to work with. We already have 8, so let's add more and fill up those octets. 10, 12, 14, 16, 18, 20, 22, 24. This is one resonance structure, and it's an ion, so we have one last step, big ol' brackets, and the ionic charge. And then you're done drawing this polyatomic ion. This one's trickier, N2O5. Nitrogen needs more bonds, so we'll put it in the middle-ish area. There are also the 5 oxygens. Each of those will also want 2 bonds. Let's see if we can make these fit together like a puzzle. Now you need to check the number of bonds. This one is going to have resonance structures. Nitrogen already has the number of bonds it needs, but not all of the oxygen atoms do. In order to see what's going to happen, we need to use a Lewis dot structure and a wee bit of math. 2 nitrogen atoms each with 5 electrons make 10. plus 5 oxygen atoms with 6 electrons makes 30, and it adds up to 40 total electrons. So far, we only have 12 in the structure. Let's count out the electrons and see where we might need a double bond. 14, 16, 18, 20, 22, 24, 26, 28, 30, 32, 34, 36. And we can only add 2 more pairs, but we'll need to make sure every atom has a full octet. 2 oxygens and both nitrogen atoms need a full octet still. So place the last 4 electrons as double bonds. It turns out that the double bonds could also be on the bottom 2 oxygen atoms, which is why these are resonant structures. It is correct to draw both structures in brackets, or with dotted lines indicating possible placement of the double bonds.